Okay, Assalamu alaikum everyone. Good evening. I hope you're all doing well. First of all, Eid Mubarak. I hope you guys had a good break. And I hope none of you guys studied because honestly, you really needed a break after all you've been through so far, to be honest. Um, Today, I'm going to talk to you guys about nucleotide metabolism. To me, this, I think, would be the perfect idea of what a first year lecture should be. It talks about basic concepts, and it also gives you an idea of clinical relevance and some medications. You know, especially if you're someone who really wants to pursue medicine or someone who really likes medicine, I think this lecture in particular honestly gives you a good glimpse while still maintaining the basics. So I really am a fan of this lecture, and this was my favorite lecture in MOL too. Overall, it's very nice, and inshallah won't be too difficult. It's supposed to be a 2-hour session. I don't think we're going to use all 2 hours. And I believe that Zahra sent you guys the slides that I'm going to use today. If you guys have those, and inshallah later you'll be sent the one with questions in it. Like now, when you look at this lecture, the first thing you might notice is that the slide number, and yes, these are 72 slides. It's good if you see that because that means your eyes are working. But don't worry, we're not going to go through every single one of these slides. I didn't delete any for your sake. We're going to be skipping through a lot of slides, and I'm going to be talking about one concept, for example, in one slide. So don't worry about the slide number. It's not going to feel like 72 slides. Let's begin. So I'm going to go away from the basics, and I'm just going to take you to the slide that I made right here. Now, in terms of this lecture, you guys talked about the basics already in MOL 1, where we talked about nucleotides in very brief detail. We talked about DNA and things like that. But the most important things from those slides that were included this lecture, the first 10 slides, I believe, are these concepts right here. You're very unlikely to be asked about them, which is why I didn't even include any practice questions on them. But I just wanted to mention them just in case. So if you do want to go through the basics, this is a very good slide to cram, even in the notes. So DNA and RNA are nucleotides. And the good thing about this is that you get a better idea of why nucleotide metabolism is important, because we're talking about the making and breaking of DNA and RNA. So nucleotides themselves, they're composed of a sugar, they're composed of a nitrogenous base, and they have a phosphate group. Now, the reason I have phosphate group in red is because nucleosides do not have a phosphate. Then we have the purines and pyrimidines. So the purines are adenine and guanine, and the mnemonic for that was pure as gold. But then we also have cytosine, uracil, and thymine. These are pyrimidines. And honestly, they're just not pure as gold. I know there's like a cut the pie mnemonic for them, but if you know that adenine and guanine are the pure as gold purines, then you know the rest are going to be pyrimidines. Now, the purine nucleosides will end in the suffix -ine, so adenosine or guanosine, and the pyrimidine nucleosides will end in -dine, so it would be uridine, thymidine, etc. We also know that in DNA, we have adenine, guanine, cytosine, and thymine. And then in RNA, we have the same thing, except instead of thymine, we have uracil. Now, the purines are composed of 2 rings, and the pyrimidines are composed of 1 ring. And this is basically all of the basic concepts so far. So, we're all up to speed right now. Also, I want to know, do you guys want to make this an interactive session, or do you guys just want me to explain and you ask at every checkpoint? You can just write it in the chat if you want. Interactive. Okay, fast. We'll interact. All right. طيب. So there is a lot of room for interaction in this lecture, don't worry. But yeah. So now let's begin with like the actual meat of the lecture. Like, now we're going to talk about the synthesis of purines, pyrimidines, and we're also going to talk about their degradation. Starting off, we're going to talk about purine synthesis. Now, we can synthesize purines in 2 ways. We can either make them from scratch, and that's called de novo, or we can use them, or we can reuse preformed bases and convert them into full-on purines and pyrimidines, and this is called salvage. So for example, when a cell dies, it releases its contents. And one of those contents would be those bases, those DNA and RNA bases. So you could take those bases and just make them brand new, So that would be how salvage works. De novo is just you're making it from scratch. And we'll go into a little more detail. Now, this guy right here, this is called 5-phosphorybasyl alpha pyrophosphate, or PRPP. This is a very important molecule. It's very, very important. We need it for both the de novo and the salvage synthesis. So just remember that PRPP is needed for both de novo and salvage. And I'll explain how. So we're going to start here. We have to get this PRPP, of course, we need to make it. The PRPP comes from this molecule called ribose 5-phosphate. Now, can someone just unmute their mic or write in chat, where does this ribose 5-phosphate come from? Like, where do we get HMP shunt? Very good. Thank you, Selma. So this ribose 5-phosphate comes from the HMP shunt. So when we have the HMP shunt, we make this ribose 5-phosphate, and that will get converted into PRPP. This 5-phosphorybosylate 1-pyrophosphate. Just remember PRPP. How do we make PRPP? What enzyme do we use? We use an enzyme called PRPP synthetase. And this process requires energy in the form of ATP. Now, we can stimulate this reaction through phosphates, and we could inhibit this reaction through purine nucleotides. Now, because we're going to inhibit this through purine nucleotides, this is what we call end product inhibition. This is a form of feedback inhibition where the thing inhibiting this reaction would be the end product themselves. And the end product in this case would be AMP or GMP. And we'll get into that, inshallah. And just so you're all up to speed with me, we're talking about de novo purine synthesis. Now here, this is just a slide to show you how everything goes. So as Selma correctly pointed out, the ribose 5-phosphate comes from the HMP shunt. And this is eventually going to form DNA and RNA after we make this PRPP, which is going to be used for salvage or de novo. And they may ask you, for example, where does this process occur? Does anyone know, or can anyone guess actually? Where does DNA synthesis and RNA synthesis occur? Like, where does this whole process occur? Or let me clarify, what organ does this occur in? The liver, very good. So this mainly occurs in the liver. So if you're asked where does, for example, de novo purine synthesis occur, this occurs primarily in the liver. Right? Also, for purines, the process requires 11 steps. And that looks something like this. Now, I know what you're thinking. You're looking at this and you're absolutely terrified. Well, you don't need to be, because we're skipping it. And I'll get back to it later. But there's a different slide where we'll talk about what's important. So yeah. Now, one thing to note about purine synthesis is that we have a ribose, and essentially we add the atoms of the purines. All right. And remember this point, that we're adding the atoms to essentially make the base. We don't synthesize the free base initially, we eventually make the base. And this is something different from pyrimidines, which we'll talk about later. Now, the first purine derivative, so after these 11 steps over here, we make this molecule called inosine monophosphate, which has the base of hypoxanthine. Now, this is the parent nucleotide. So I just want you to remember that IMP is the parent purine. The end product of purine synthesis should be AMP and GMP, because we will convert this IMP that we make into AMP and GMP. Right? So IMP is the parent, and AMP and GMP are not the children, the end products. Right. Now, what do we need to know here? Luckily for us, not much. So you're going to be asked about the synthesis of PRPP, of course, and we already talked about that. Can someone remind me, how do we make PRPP? All right, I'll give you guys some time just to answer. And it's fine, you can say I don't know. There's no problem with that. Okay, very good. So we add, so what we do is we use ribose 5-phosphate, and it's going to be converted through PRPP synthetase into PRPP. Like the other thing you need to know with this PRPP is the next step. This is the rate limiting and committed step, which is where we convert this PRPP into 5-phosphoribosylamine. And we use this really weird enzyme, which we'll get to later. So these are the only two steps that you need to know in terms of purine synthesis. So the first step, which is making the PRPP, and the second step, which is converting it, and the rate, which is the rate limiting and committed step. Right. Now, I asked you guys to remember that we need to make, that we don't make the base initially. We add atoms and eventually make the base. Now, the atoms that are being donated are carbon and nitrogen, and they are donated from 5 molecules: glycine, aspartate, glutamine, carbon dioxide, and tetrahydrofolate. So another way they like to suggest that you remember this is GAG, carbon dioxide, tetrahydrofolate. So how could you remember this, for example? Really, GAG is this GAG, carbon dioxide, tetrahydrofolate is the easiest way to honestly remember it. And again, they are donating these molecules to ribose 5-phosphates. Now we're going to get into this this phosphoribosylamine step. So what are we doing? We're converting this PRPP into 5-phosphoribosylamine. And this is the rate limiting and committed step right here. So the conversion of PRPP into 5-phosphoribosylamine, this is the committed and rate limiting step. Now, one thing to know is that PRPP stimulates this reaction. So when we have PRPP, this will stimulate the reaction. And this is what we call feed-forward stimulation. And then we also have inhibitors, which are AMP and GMP. Now, AMP and GMP are the end products, and they inhibit this reaction right here. So what do we call this inhibition right here? Could someone please tell me? Feedback, very good. This is feedback inhibition, but with very specifically, yes, end product inhibition. So this is feedback inhibition, but in the form of end product inhibition. Very good to the both of you. So yes, one last thing I'd like to point out, this reaction requires glutamine, not glutamate. Now this is a very easy point to confuse. So this reaction requires glutamine, which ends in INE, and not glutamate or glutamic acid. So this reaction requires glutamine. So let's recap. We have the PRPP. This is going to make the 5-phosphoribosylamine through this very weirdly named enzyme. This process requires glutamine, not glutamate, glutamine. In order to, we can activate this through feed forward of PRPP, and there's end product inhibition through AMP and GMP. Right. So yep, we've already talked about all of this. Now, for steps 3 to 11, essentially we are making IMP, as I've mentioned before. Another thing to note is that in 2 of these steps, which if I'm not mistaken, are step 4 and step 10, they require this molecule N10 formyl tetrahydrofolate, or N10F-THF, right here. And I'll show you where that happens. So yeah, step 4 and step 10. So this N10 formyl tetrahydrofolate, or N10 formyl THF, this is going to be converted through formyl transferase, but you don't need to remember the enzyme in particular. Just know that 2 steps require tetrahydrofolate, or N10 formyl tetrahydrofolates. And we'll talk about why that's important in a bit. Now that we've made this IMP, we made the IMP, what do we want to make now? Could someone tell me in the chat? AMP and GMP, thank you. So yes, we make this IMP because we want to make AMP and GMP. So to make GMP, we need 2 enzymes. We need IMP dehydrogenase and GMP synthetase. I know there's a lot of enzymes. Don't panic. I'm going to tell you guys an easy way to remember it. That will help you guys. So we have this IMP right here. We need to convert into GMP. We use 2 enzymes, IMP dehydrogenase, which makes xanthine monophosphates, or XMP, and this will then be converted to GMP by GMP synthetase. We also can convert it to AMP through adenylosuccinate synthetase, and then further into adenylosuccinase or adenylosuccinate lyase. So what this means is that we have to make adenylosuccinate and then break it essentially into a better form, which is AMP. Now, how can we remember this? It's a lot of enzymes, a lot of weird names, a lot of synthetase or A's, way too much. Easy way to remember it. If you want to make GMP, the enzyme will have the word GMP or IMP in it. If you want to make AMP, it will have the word adenylosuccinate in it. Does that make sense? Like that, does that way of remembering it make sense? Okay, cool. Great. Like another thing to note is that these steps right here, this IMP dehydrogenase and this adenylosuccinate synthetase, they are feedback inhibited. And yes, that would mean that they are also end product inhibited because AMP and GMP, the end products. But it's a little different than the other steps. You see, the point of this inhibition right here isn't because we want to stop making it entirely, but because of some sort of imbalance. So in our body, we have everything in a normal ratio. The ratio of, for example, there are certain lengths and certain ratios which we need in our body in order to maintain life. And the ratio of AMP and GMP, so there's this ratio level. Let's say we have less AMP than we need, or we have more GMP than we need. The GMP is going to inhibit itself from being formed so that it balances out with the AMP. So the feedback inhibition, yes, it is feedback and it is end product inhibition, but the point is for balance, not just to stop the reaction. But again, generally you stop reactions because you need to bring balance in the body, but that's for the philosophers to talk about, I guess. Now, one thing I'd like to point out is I mentioned earlier how this lecture to me is great because you get clinical aspect and you get drugs as well as the basics. Now let's talk about the drugs. So the first drug we're going to talk about is something called mycophenolic acid. Mycophenolic acid. This can also be called mycophenolate. Mycophenolic acid. This drug is going to inhibit this enzyme right here. This is called IMP dehydrogenase. Now, we use this drug to inhibit our cells or our immune cells from causing an immune reaction when we want to transplant organs. So I'm sure most of you guys, if not all of you, know what an organ transplant is. And this process our immune system may not like that we're doing this. And you'll learn a lot about this next year. It's really fun. But what happens is that we give this drug to patients so that their body does not reject this organ, if that makes sense. So yeah, we've mentioned this stuff here. I don't see the word methotrexate, but this synthesis of tetrahydrofolate is inhibited by a drug called methotrexate, and it does come in another slide. Methotrexate is another important drug that you definitely need to remember right here. So methotrexate inhibits the synthesis of this molecule right here, tetrahydrofolate. And if you remembered, we need tetrahydrofolate because it's important to make DNA and RNA. Now, methotrexate will inhibit an enzyme called dihydrofolate reductase. Dihydrofolate reductase, or DHFR. So what this will do is that when we inhibit this enzyme, we are not going to make tetrahydrofolate. This also means that, as you can see here, we will have less folate as well. So the body will kind of deplete in folate. And I remember in our year, they asked us a question about if a patient is given methotrexate, what should you give them? Now, for us, the answer was folate, but there is another drug. This is a fun fact, by the way. You don't need to remember this in particular. But when a patient takes methotrexate, you should also give them folinic acid or leucovorin, and this prevents them from having a folate deficiency. And do you guys remember, I think it was in MSK, why you don't want a folate deficiency? Like what could happen to a baby, for example, if they don't get enough folate? Spina bifida, very good. Never forget this. You will be asked about spina bifida in every year. Not this exam, but just for the future, don't forget what spina bifida is. It can be very important. So yeah, we give this drug methotrexate for conditions such as cancer. We can give it in rheumatoid arthritis. The thing is, methotrexate is kind of stupid, meaning that we have cells that we want to stop. And the thing is, we just stop all of the cells as a whole. The idea is that you have some for it said there's some bad people there. Let's just get rid of everyone. So we get rid of the bad people. And because of this, there will be side effects such as macrocytic anemia, the skin will be scaly, you'll have GI problems, immunodeficiency, baldness. So it's important to understand not these side effects in particular, but why they happen. And that's because all of the cells are affected when you give methotrexate, not just the cancerous or the autoimmune cells. We have another drug, which is quite similar, and this is called trimethoprim. Trimethoprim is an antibiotic. It also inhibits dihydrofolate reductase. And as you could imagine, because of this, it also has similar consequences in the sense that all of the cells are affected, both the bacterial and the human cells. And then we talk about this other drug, sulfonamides. So sulfonamides compared to trimethoprim is a much better drug, for the reason being that in terms of side effects, you won't have the same ones as trimethoprim, because you're inhibiting a step that's not found in humans. It's called dihydropterate synthetase. Dihydropterate synthetase, DHP synthetase. So sulfonamides inhibit this step, and this step is only found in prokaryotes or bacteria. And this is better for us in a sense that if we give a patient sulfonamides, for example, they wouldn't have the side effects of trimethoprim, because trimethoprim will affect both human and bacterial cells, whereas sulfonamides will only affect bacterial cells. And again, knowing these drugs is very important. Now, this is the most dense part of the lecture, like all of the stuff about de novo purine synthesis. I understand it can be very dense, and I'm very happy that you guys are, or at least I could only imagine that you guys are still awake till now. So far, are there any questions? All's clear. All right, this is one person saying everything's clear. I want to at least hear another person. Okay, great. Thank you, guys. Now, I want someone, whoever's comfortable with unmuting their mic, I want you guys to I want someone to summarize, or sorry, whoever's comfortable with unmuting their mic, I want someone to summarize the things we talked about. And I'll give you a template for how you should remember it. First of all, the steps in purine synthesis, and secondly, the drugs we talked about. But does anyone just want to you don't have to go full details, just very briefly. What did we talk about? Okay, that's fine. I'll just summarize it myself. I'll tell you guys just the important details that we talked about in a very brief nutshell. So we talked about, first of all, we focused on de novo purine synthesis. We focused on the first two steps of the reaction. First one being the making of PRPP through PRPP synthetase. And this comes from ribose 5-phosphate, which comes from the HMP shunt. You can stimulate this by phosphate, and you can inhibit this through end product inhibition. The same applies to the second reaction, which is the conversion of this PRPP that we just made into 5-phosphoribosylamine. And in order to do this, this requires glutamine. And this is end product inhibited as well as simulated by PRPP. From there, we eventually make the parent, which is IMP. And IMP then gets converted into either AMP or GMP. We talked about 4 drugs, the 4 drugs being myclophenolate, which inhibits IMP dehydrogenase. We also talked about methotrexate, which inhibits dihydrofolate reductase. Trimethoprim, another drug we talked about, also inhibits dihydrofolate reductase. And then we also talked about sulfonamides, which inhibit dihydropterate synthetase. And because of this, sulfonamide is not going to have the same adverse effects, and it's considered a lot safer. That's just a brief summary. Again, this lecture is recorded, so feel free to go back to this as you please. But in terms of actual contents, we're pretty much done with a big half. Now I do need someone to unmute. I have a question. So I want someone to help read this question and answer it. Who can volunteer?
I can do it.
Okay, great. طيب, could you read the question?
Okay, so what is the end product of de novo purine synthesis?
Like, what do you think is the answer?
C, GMP.
Very good. طيب, why is it not B?
Because IMP is eventually converted to GMP and AMP, I think.
Very good. Very good. Yeah. So IMP is just a step. It's not the end product. It's a parent, but it's not the thing that we're essentially trying to make at the end. The end product is GMP. Very good. Thank you so much.
Thank
Like,
you.
now we're going to talk about the purine salvage pathway. And when we're done with this, I'll give you guys a 10-minute break because I know you need it. So let's talk about purine salvage. So again, like I mentioned, purine salvage is when we recover the bases. So when a cell dies, they release bases. We can pick them up and just convert them back into nucleotides. And this process is called phosphoribosylation. Now, one thing you have to keep in mind is it's a lot easier for the cell to salvage the purines than make its own, because they already have been made. All you have to do is convert them through a reaction and set them up. That's pretty much it, as opposed to making something from scratch. That's something to keep in mind, but I don't think it's too important for you to know. What is extremely important, what I cannot emphasize enough on, is this slide right here. This slide is incredibly important. And of course, Yani, the clinical conditions related to the slide, which we'll talk about later. But we have two enzymes, APRT, adenine phosphoribosyltransferase transferase, and HGPRT, hypoxanthine guanine. Now, HG for hypoxanthine and guanine, A for adenine. So we have three bases. We have an adenine base, we have a guanine base, and we have a hypoxanthine base. Now, adenine can be converted to AMP, guanine to GMP, and hypoxanthine to IMP. And as I mentioned in the very beginning, PRPP is not just important for de novo, but it's also important for salvage. In purines, in order to make a purine, you need to have PRPP. So what do? We get this adenine, and along with the PRPP, we will make AMP. And the enzyme that does this is this APRT. For guanine and hypoxanthine, they both require PRPP, and they require HGPRT, which will convert them into their respective nucleotides, which would be GMP and IMP. So APRT makes AMP, HGPRT, if it's converting guanine, will make GMP, and if it's converting hypoxanthine, will make IMP. I really hope this is clear. If it's not, let me know. I will repeat this. But you really, this is really important. Is this clear? Okay, sure, I'll repeat. So in order to salvage a purine, we need PRPP again, not just for de novo, also for salvage. And we have two important enzymes. We have this APRT, and we also have the HGPRT. The APRT is responsible for converting adenine into AMP with the help of PRPP. For hypoxanthine guanine, for HGPRT, it converts guanine into GMP along with PRPP, and it also converts hypoxanthine into IMP along with PRPP. So HGPRT is responsible for converting guanine and hypoxanthine into GMP and IMP respectively. So guanine to GMP and hypoxanthine to IMP. And APRT is responsible for converting adenine into AMP. And all of these reactions need PRPP. If you want to make a purine, you need PRPP. Is it more clear now? All right, perfect. So that's for this. Now with here, I know this slide kind of looks a little bit confusing. Don't worry too much. I want you to focus on the top half because that top half is important. So everything we've made so far right now is a ribonucleoside, not a deoxyribonucleoside, a ribonucleoside. We need to make deoxyribonucleosides because, of course, we need to make DNA. So how do we do this? We use an enzyme called ribonucleotide reductase. Now, one thing I'd like to mention, and I think you guys, I think Dr. Ahmed Jada may have mentioned this, for example, in his enzymes lectures, but if you know the meaning of the enzyme's name, or if you know like what the name of an enzyme means, you know its function. And this is something that could be extremely useful for you. Like you would know what the reaction is going to be, at least, or have a general idea of it before even studying it. From the word reductase, I know that something is being reduced, for example, from not deoxy to oxy, or from oxy to deoxy. So in this case, this is from ribo to deoxy, because when you reduce something, you remove the oxygen from it. And that's what's happening in this reaction right here. It's just food for thought. You don't need to know this in that much detail, but it might help you. If you see an enzyme and you think you might be able to understand what it means, try do that. It could save you a lot of time and it could help you. You never know. So ribonucleotide reductase, this is going to reduce this ribonucleoside diphosphate into deoxyribonucleoside diphosphate. We are removing this O and just leaving it as an H. We're removing the oxygen. So it becomes deoxy. And this can be inhibited by deoxy ATP. Like, is this clear? Because I know this slide, I remember looking at the slide in first year, I remember how confused I was. So I just want to make sure you're all with me. This is for both de novo and salvage. Yes, yes, it is. So everything we've made is a ribonucleoside. So whether it was de novo or it was the salvage pathway, all we've made is ribo. We have not made deoxyribo. That's a really good question. Thank you very much. Okay, so I think we're all clear here. Last thing I'd like to mention is that we have a drug called hydroxyurea. Hydroxyurea could be given in sickle cell. Okay, question. What kind of anemia is sickle cell? You guys took heme, I expect you guys to know this. What kind of anemia is sickle cell? It's not relevant to the lecture in particular, but I just want to see if you guys remember this. You can write it in chats. Microcytic hypochromic, very good. I really missed heme. Heme was a wonderful block. But hydroxyurea can be given in sickle cell patients. It can also be given as an antineoplastic. The idea here is that we want to inhibit this DNA from being formed. And this applies to all of these antineoplastic drugs. The idea is when a cell divides, its DNA divides. If a cell does not have DNA, it will not divide. When we inhibit, for example, the rationale behind hydroxyurea is that you want to inhibit this DNA synthesis, and in doing so, you would kill off the cell. So that's why it could be used as an antineoplastic agent. All right. So this is our next checkpoint. I hope we're all clear so far. Does anyone have any questions? Anything you'd like to ask? All clear? I'm going to need a volunteer for the next. I have a question to ask you guys, and I need a volunteer who would like to unmute their microphone. So just someone please volunteer. And this is the question. And it's okay to not know it. This is just your opportunity to learn. It's better to answer something wrong now than on the exam. I really encourage anyone to volunteer. All right, that's fine. I'll read it. Okay, class. We'll just stick with chat. So sulfonamides have an effect on DNA synthesis, but are considered safe. Why? So someone said B. Do you guys agree with this person? Okay, someone said B and someone said C. Do you guys think it's B or C? Okay, another person says C. C. Okay, yes, so the correct answer is C. It only targets bacterial DNA, leaving human DNA unharmed. Let me go back to that slide just to show you. This might take a while. Oh, wait, no, we're here. Okay, so right here, So trimethoprim, for example, we said that it's an antibiotic that inhibits this step. This is found in both humans and prokaryotes. Now, sulfonamides, on the other hand, they will target a step that's only found in bacteria, which would be dihydroxyapatite synthetase. It's all right. Again, as I mentioned, get it wrong now, don't get it wrong on the exam. But very good. Thank you, guys. Like, do you guys want a 5-10 minute break? Just go stretch, get some water. Okay, Khas. What time is now? It's 7:41. Let's come back at 7:50, all right? All right. So we're pretty much done with more than half of the lecture, and everything from here is pretty much smooth sailing. This is honestly my favorite part of the lecture. We're going to talk about purine degradation, and then we're also going to talk about some clinical conditions that are very important, and I'd really emphasize that you remember them. Oh, sorry, Mike. Forgot to turn my camera on. Oh, okay. Okay, yeah. So let's start off by talking about purines. So we've made the purine. Now, sometimes we need to get rid of this purine. And so the end product of purine nucleotide degradation is something called uric acid. Uric acid or urate. Uric acid or urate. Uric acid is very important because it's going to have a lot of clinical correlations, and we're going to talk about something called gout. So there's a lot to talk about. But basically what will happen is that AMP and GMP, when they want to degrade, they will essentially become uric acid. And this usually should get excreted through the urine. Now, maybe that whole process doesn't go too well. Maybe something goes wrong. Maybe we make too much uric acid to the point where we can't excrete it. Or maybe we just can't excrete it because of a problem there. When this happens, we will have uric acid in the blood. And when we have uric acid in the blood, we call this hyperuricemia. Hyperuricemia. This means we have too much uric acid in the blood. So just to break it down, hyper means too much. Uric refers to uricemia, or sorry, uric acid, and emia refers to in the blood. So there's too much uric acid in the blood. And this can cause problems. And when we have hyperuricemia, one of the conditions we can get is something called gout or gouty arthritis. So arthritis is inflammation of the joint, and it's usually very painful. And gouty arthritis, this is due to the deposition of something called a monosodium urate crystals, and this is a result of the hyperuricemia, and this leads to the arthritis. So usually this is because of underexcretion in most individuals who do have hyperuricemia. And I'm going to come back to these slides and tell you very big hints that you should pay attention to when you see that someone has, or when you might want to think that this person has gout. Now, they may show you this picture. This guy has gout. This is, I believe this is a bifurcation stain. So, and this right here, this thing right here, this is called a tophi. And the patients would have pain in this joint. And so they'd have gouty arthritis in this joint. Now, gout, when you want to treat it, if someone's having an acute attack of gout, you give them an anti-inflammatory, like an NSAID or whatever. But in long-term or chronic, we use a drug called allopurinol. Now, this is like from this, I think this whole section, the most important drug to remember is allopurinol. There are other drugs, but allopurinol is very important. So allopurinol is a non-competitive inhibitor of xanthine oxidase. Non-competitive, meaning it's not going to bind at the same binding site. It's going to completely block it off. It's going to permanently bind. And it's going to inhibit this enzyme called xanthine oxidase, which converts xanthine or hypoxanthine into uric acid. And I'll show you a picture of that very soon. Now, the risk of gout is increased by eating meat and seafood. So I don't know how many of you guys took English with Dr. Charles, but he did mention the word gout once. And he called it the disease of kings, because kings like to drink alcohol. Alcohol is another risk factor, but don't worry about that. But they love to eat meat. So Meat is a risk factor. Seafood's a risk factor. Yeah. Now, this is the picture I want to show you right here. Allopurinol acts on this part right here. So let's say we have too much uric acid being synthesized. This would be due to uric acid due to overproduction. This isn't as common, but this is what we want to show. And what this will do is that so we have this enzyme called xanthine oxidase, which will make this uric acid. We want to block that. We want to block the xanthine oxidase, and we don't want it to work. So xanthine oxidase acts in this arrow and this arrow right here. So we use allopurinol. Wherever there's xanthine oxidase, allopurinol will act. So hypoxanthine will not be converted into uric acid, and xanthine will not be converted into uric acid. Now, is this good or bad that we're not converting hypoxanthine and xanthine into uric acid? Someone answer me in the chat. Do you think this is good or bad? Good. Does anyone think it's bad? Or anyone else that thinks it's good? Good if there's hyperuricemia? Yes. All right. So yes, this is good. Now, you're probably wondering, like, this is good. But why? So hypoxanthine and xanthine are a lot more soluble than uric acid. So because they're more soluble in blood, we won't like, for example, have hypoxanthenemia or hyperxanthenemia or whatever. No, it's soluble. So we won't, it's good. Now, let's say we're dealing with urate excretion. Now, it's more preferred in this case that we have two drugs, probenecid and sulfonylurea. They enhance the renal excretion, but they don't affect the production of the they don't affect the production. So generally, if we want, but again, just emphasize on allopurinol. Allopurinol, non-competitive inhibitor of xanthine oxidase. You give it in chronic gouty arthritis, and it prevents the formation of uric acid in the first place. Now, that's it for just gout in general. I want to show you some really important hints that when you see these words, these buzzwords, I want you to think gout. So they may mention that he has high uric acid. They may mention hyperuricemia. But more importantly, they will say words like crystals. They may say arthroscopy. They may say arthritis, arthrocentesis. They may refer to the joints in some sort of way. They may show you this picture. They may say he has something on his big toe, a tophi on his big toe, or he has pain in his left big toe. They may show you, they use the word UV or bipharyngeals. They may show you this picture. They may say he's a male, he's old, he likes to eat meat and drink alcohol. So if you see these words, I would say in this context of gout, there's a 99% chance that the question they're asking you about in this exam is about gout. And how do we treat gout? The main drug you need to remember is allopurinol. This is a non-competitive inhibitor of xanthine oxidase for long term. Acute is anti-inflammatory, but focus on allopurinol. Okay, now we have another condition. This is called TLS-associated hyperuricemia. So this is tumor lysis syndrome associated hyperuricemia. Now, what happened? This is actually a side effect of chemotherapy. Now, in chemotherapy, we're killing these cells. We're degrading their nucleotides, if you remember. Like, we're not letting the DNA aslan be formed. We're not letting these nucleotides be formed. We're breaking them off. So there's going to be nucleotide catabolism. As a result of this, when we want to break down a purine, for example, what are we going to have a lot of in the blood? Someone answer me in the chat. If we break down a purine, like if we keep breaking down purines, what do we expect to happen in the blood? Uric acid, very good. So there will be uric acid in the blood and there will be too much. So this would be hyperuricemia. So tumor lysis syndrome, this is a side effect of chemotherapy. This is a result of the catabolism of purine nucleotides in the cancer cell. And this will lead to hyperuricemia. Now, there are a lot of words on the slide. And if you're like me, you don't like looking at a lot of words. So let me summarize this all for you. Now, who told me about who mentioned HMP shunts? I think it was Selma, maybe? Yes, it was Selma. Selma mentioned the HMP shunt. So did you guys study von Gerke before? Okay, so von Gerke is a disease, or yeah, it's a condition where we have accumulation of G6 phosphates, glucose 6 phosphates. This glucose 6 phosphate is going to go into the HMP shunt. As a result of it going to the HMP shunt, what do you think we will make? What are we going to make?
Ribose 5-phosphate.
Thank you, ribose 5-phosphates. When we make ribose 5-phosphates, what else will we make after that? PRPP. What do you guys see where I'm going with this? So we're making ribose 5-phosphate, then we're making PRPP. Essentially, we're going to have AMP and GMP because we're going to make nucleotides as a result of this. The problem is these are nucleotides we don't need. And if we don't need something, we break it. When you break a nucleotide, again, what will you have? What will we make? Uric acid, very good. So we will make uric acid. And because of this, the point they're trying to make is that in von Gerke disease, they're more prone to have gout because they'll have hyperuricemia. All right, that's essentially what they want. That's the zubda of the situation. Right. Now they talk about, now there are two other diseases. This is a disease called Leach-Nyhan syndrome. This is a very bad disease. Characteristically, these patients, they will try bite their fingers or their lips off from how much pain they're in. But this is a really, really bad disease to have. This is X-linked recessive, and it affects an enzyme called HGPRT. Now, can someone remind me, what does HGPRT do? Like, what pathway do we use HGPRT in, and what does it convert what into what? So first of all, what pathway? Salvage. And what does it do? What does it convert into? Like what does it convert X into Y? Guanine and hypoxanthine salvage, yes, into GMP and IMP. So that's what they're responsible for doing. In this disease, there is no HGPRT. So this reaction right here is not happening. Instead, we have a lot of this. So what's going to happen as a result is that there's this PRPP, which is normally used to make IMP and GMP. It's not going to be used. It's going to drive this reaction right here, which will make AMP. And we will have way too much AMP, way beyond what we need. And so as a result of this, because we have too much AMP, we're also going to break down. And as you guys have, I'm not going to ask you guys to say it again, because I think you understand that when you degrade a purine, you make uric acid. So these patients will have hyperuricemia. If they have hyperuricemia, they may also have gout. And there is a mnemonic to remember it. HGPRT also tells you the symptoms, which is hyperuricemia, that's H, G for gout, P for pissed off, R for retardation, as in mental retardation, and T for tone decrease, as in hypotonia. And again, the characteristic is that they're mutilating themselves. They're biting their fingers off, or they're biting their lips off. It's really bad. So here it is again. And here's just a picture that they're mentioning all of this on. So yeah, you can literally see they're mutilating they're mutilating their fingers. It's a very bad disease to have, and it's quite scary. And yeah, we've already mentioned all of this. Last disease, I know this slide looks scary, but really we just care about this. So in the so when we want to degrade a purine, one step of the pathway is converting adenosine into inosine, which will eventually form hypoxanthine, xanthine, whatever. So what can happen is that we have this enzyme, adenosine deaminase, which converts adenosine to inosine. If we have a deficiency in this enzyme, what we will have is a disease called SCID, severe combined immunodeficiency. What will happen is that as a result of this, we will have no T and no B cells. We will have lymphocytopenia. All right, so the B and T cells, they're gone. And there will also be large buildups of deoxy ATP in the blood. But what's more important to remember is that they will not have immune cells. Because of this, they can't fight infections. So a lot of these patients die before the age of 2 because of an infection. All right. And that's all of the diseases that we need to cover in terms of that section. I know it was a little bit bulky, but again, you can go back to it. But let me just recap a few things just for your sake. So again, in the purine degradation pathway, we have to make uric acid. The goal is we degrade these purines and make uric acid. If we have too much uric acid or too little uric acid, this could cause hyperuricemia, which will lead to gout. And I told you guys the characteristics of a patient with gout. To treat a patient with gout, in acute attacks, we can give them NSAIDs or any sort of anti-inflammatory. And in chronic, we can give them a drug called allopurinol, which will non-competitively inhibit xanthine oxidase. And as a result, we will have xanthine and hypoxanthine in the blood, and they're more soluble, so this won't be a problem. Now, we also talked about TLS-associated hyperuricemia. This is a side effect of the chemotherapy. We also talked about how von Gerke patients are more likely to have gout because they will have buildup of G6P, which stimulates the HMP shunt, which increases the amount of AMP we're going to have, or nucleotides we're going to have, and it's going to have the whole catabolism that we've mentioned. We also mentioned Leishman LNS. This had the symptoms of HGPRT, and they're characteristically biting their fingers off, they're mutilating themselves. And then we also talked about SCID, which is a result of adenosine deaminase deficiency. I know I say it sounds like it's not a lot. I'm going to say that it sounds like a lot, but it's a lot easier than it seems. But I'm not going to say that because I'm sure that's not what you want to hear right now. But up till now, are we okay? All right, I got a thumbs up. I got a yes. Great. If you have any questions, now is the time before I ask you guys a question. Okay, great. Alhamdulillah. Right. Now here's a question. We have a 6-month-old girl who has some developmental delay and is biting her lips and fingers. She is diagnosed with Leishman syndrome. This child cannot metabolize which of the following? Okay, who wants to answer in the chat? Oh, okay, we got an answer. E. All right, does anyone agree? Does anyone disagree? Okay, so someone said E. What do you guys think? All right, another person said E. All right, 3 people said E. E is the correct answer. For just 2 things to mention, I could flip this question, by the way. I don't have to mention that she's diagnosed with Leishman syndrome. I could say she has developmental delay and is biting her lips and fingers. And I could say that most likely she cannot metabolize which of the following. The only right option, when I said self-mutilating, is characteristic, at least in this context, for Leishman syndrome. So they're in Leishman, they don't have HGPRT, so they cannot metabolize hypoxanthine. I could also change this question up by putting guanine instead of hypoxanthine, and the answer would still be correct. All right, now pyrimidines. Pyrimidines are way easier than purines. It's a lot easier to remember pyrimidine metabolism than purine metabolism. In pyrimidines, there are 6 steps. You make the base and you add on to it, and it's a lot simpler. It's a lot calmer. So you make the base, and essentially you're doing all of this to make UMP. UMP is the parent. So uridine monophosphate, this is the parent that we want to make. Excuse me. And there are 2 precursors in this case, aspartic acid and glutamine, but carbon dioxide can also donate some atoms. And the first step right here, in terms of this reaction, is making carbon monophosphate. So I think you guys took the urea cycle. And so you notice that this word CPS2, we have 2 CPSs. We have CPS1, which is for the urea cycle, and CPS2, which is for pyrimidine synthesis. There's this slide right here. I'm not going to cover the slide here, but when you're reviewing for your final, please make sure you go through the slide. It's an excellent point to review, and this is a good point where they can ask you guys questions. I would recommend that you do look at this table when you're studying. Back to this, the enzyme that makes carbon monophosphate is something called CPS2, carbon monophosphate synthetase 2. So what will happen is that we'll have CPS2, and this will make carbon monophosphate. Also, something to note is that this is end product inhibited by the molecule UTP. So UTP will inhibit CPS2, and this is a feedback inhibition in the form of end product inhibition. Yeah. think that's it for that slide. Then we have, this is the big picture again. Don't be intimidated. This is the only step we're going to talk about in like, this is one of the only steps, sorry, that we're going to talk about. This step right here, the aspartate transcarbamylase, I don't want you to know this step. I want you to remember this enzyme. The reason being is that in humans, the regulating step is this right here. In bacteria, the regulating step is the aspartate transcarbamylase. All right. So, and this is a point where they could ask you questions, for example, like a prokaryote is trying to make pyrimidines. What is the regulating step? And the answer would be aspartate transcarbamylase. Yeah. So, but in humans, it's the making of carbon monophosphate through CPS2. Another thing I want you guys to know is this bottom part right here, the orotates, OMP and UMP. So orotate is converted to UMP by UMP synthase. But if you look at this line right here, there is no UMP synthase. And you're probably thinking, yeah, Raffi, you probably skipped a step right here, this OMP. You probably forgot about it. So here's an interesting thing. This UMP synthase is a polypeptide, which actually has two enzymes. It has this enzyme right here, orotate phosphoribosylate transferase, these names are so long, and OMP decarboxylase. So OPRT and OMP decarboxylase. So orotate is converted to OMP by orotate phosphorylate transferase, and OMP is then converted to UMP by OMP decarboxylase. So this is the conversion of orotate to UMP by UMP synthase. Does this right here make sense that these two are part of the same enzyme, and that we use this enzyme to convert orotate to OMP, and we use this enzyme to convert OMP to UMP, but they are parts of the same larger polypeptide, which converts orotate to UMP. Does that make sense? Okay. Someone said yes. If it doesn't make sense, I will repeat it, because I know this can be confusing. Do we have to know the names of the enzymes? I think it is important that you know the names of the enzymes. And the reason being, let's say they ask you, for example, a question about, okay, so there's a condition we're going to talk about, orotic aciduria. They may ask you about one of these enzymes, for example. So just remember, OPTR, OMP are a part of UMP. Here's a weird way to remember it. I don't know if it will help you, but if you put two O's together, like OO, it sounds like a U, like oo and a U, which also sounds like oo. I don't know how useful this is. I honestly just came up with this on the spot. And I do hope that what I'm saying does make sense and that I don't sound crazy right now. But basically, so UMP synthase is composed of OPRT and OMP decarboxylase. So I would say remember them just in case. Most likely they'll stick to UMP synthase, but if you can remember them, remember them. That's what I would suggest. Yeah. Like, okay. So now let's say we have this UMP synthase. We said UMP synthase converts orotate into UMP. Let's say we block this enzyme. What do you guys think will happen if we block this enzyme right here? If we block UMP synthase, accumulation of orotate, too much orotic acid. Very good, very good. So we will have too much orotic acid, and this will go in the urine. So we call this orotic aciduria. So I told you guys before, like, for example, if we have something emia, that means it's in the blood. Well, if we have something uria, like URIA, this means that it's in the urine. So we have orotic aciduria. This means we have too much orotate in the urine. So let's say the UMP synthase as a whole is blocked, or one of these two parts is blocked. The patients will have orotic aciduria. Now, the patients could have a megaloblastic anemia. The patients could be fatigued and tired. But what's more important to know, rather than the symptoms, is the treatment, which is a metabolite called uridine. So to treat orotic aciduria, we give uridine. And orotic aciduria is the blockage of UMP synthase or any of its components. Does that make sense? I'll repeat very shortly just in case. But if we have a blockage of UMP synthase, as you guys said, we'll have too much orotic acid in the urine. This is called orotic aciduria. What will happen as a result is that the patients will experience fatigue and they'll have megaloblastic anemia, and they will have too much orotic acid in the urine. And to treat this, we give the metabolite uridine. In terms of the UMP synthase blockage, it may be the UMP synthase itself, or it may be one of its components, which would be OPRT or OMP decarboxylase. All right, now, do I make sense? Does giving uridine decrease the orotic acid, or does it only give the product that's not being made? All right, so that's a really good question. So wait, honestly, I didn't understand what you meant at the end, honestly. Does giving uridine decrease orotic acid, or does it only give the product that's not being made? I didn't quite understand what you meant at the end there. Okay, I will mention what uridine does though. I didn't understand your question, but I believe you do want to know what uridine does. What uridine does is that, so for example, because we have this orotic acid, it's being excreted, and this is bad. We don't want this excretion because this excretion itself is affecting us. So what we do is we give uridine, and this uridine will stop the excretion, and it will also correct the anemia. Do you think that this is the answer you're looking for, or would you like me to, or would you like to clarify, or? Okay, perfect. It makes sense. Thank you. Is this end product inhibition? So the step that's end product inhibition is this right here, the carbonyl phosphate synthetase. This is the only thing we mentioned that has end product inhibition. All right. So now, we've already covered this. And now we talk about this enzyme called thymidylate synthase. So thymidylate synthase is it's going to convert DUMP into DTMP. Now you're probably looking at me wondering, what the hell am I saying? What is DTMP, DUMP? I'll show you a picture of it. But one thing I'd like to remember is that thymidylate synthase is targeted by a drug called 5-fluorouracil. And this reaction of making thymidine will require THF. And I'll show you what that looks like. This picture right here is where I'm going to do the explanation. So as you see, we have this DUMP. Like this DUMP, like again, eventually we've made everything. Now we have DUMP. This DUMP needs to be converted into DTMP. So how do we do this? We use an enzyme called thymidylate synthase. And this could be inhibited by a drug called 5-fluorouracil. So 5-fluorouracil will convert this will inhibit the conversion of thymidylate synthase, and therefore we will not have DUMP being converted to DTMP. Now this reaction also requires dihydrofolate reductase. So can someone please remind me, what is the dihydrofolate reductase inhibitor that we generally use for autoimmune conditions or cancer? Someone asked a very good question about this drug. Methotrexate. Very good. So yes, methotrexate. So let's say, again, this is a principle for anti-cancer therapy, for example. So the idea is we're preventing this conversion right here. So we could give methotrexate and or thymidylate synthase. And the idea is trimethoprim. Okay, yes. Wait, let me finish this. I'll get to you. So the idea is we can give methotrexate to inhibit dihydrofolate reductase. We can give thymidylate synthase to block this. And this is an idea where we basically prevent the formation of DNA. So the goal of this is to stop DNA from being formed. As for your question about trimethoprim is a dihydrofolate reductase inhibitor. You're absolutely correct. However, trimethoprim is an antibiotic. So we use it in bacterial infections. And yeah, this is a picture of it. Last thing is this. So we talked about the synthesis of purine. We talked about the synthesis of purines. We talked about thymidine monophosphate TMP synthesis. This thing that we just discussed in the previous slide. And this is what we use dihydrofolate reductase or tetrahydrofolate for. And like you guys actually mentioned, sorry, that methotrexate inhibits this dihydrofolate reductase. Now, we are done in terms of lecture content. However, there are some summaries I do need to go through with you. And there are some questions I do have that I will ask you guys and you can answer in chat. But is there anything until this point that you're not clear about? Please ask now. All right, I'm going to assume no one has questions. Okay, great. طيب. Now we have this case. Oh wait, someone may have had a question. Okay, perfect. Okay. So a 2-year-old baby boy is lethargic, weak, and anemic. His urine contains an elevated level of orotic acid. Activity of UMP synthase is low. Which of the following will be used to treat him? So can someone please answer this in the chat? Wow, that was quick. E. Someone said E. Do you guys agree with Selma? All right. 231250 also says E. Okay, great. But Selma, can you write in the chat why we give what is uridine going to do? What's the goal of uridine? Because you asked this question. But you are right, it's E. Do you remember why we give uridine? It causes less excretion of orotic acid. Very good. And it also corrects the anemia. So very good. Thank you, Selma. Now, they could flip this question on you, for example. They may not mention that he has elevated level of orotic acid. They may also not mention that they may mention, for example, either he has high orotic acid, or they may mention UMP synthase is low. They don't need to mention them together, because if one is true, the other is true. Either way, if this question didn't have activity UMP synthase is low, the answer would still be uridine. They didn't say elevated level of orotic acid, you still say uridine. Now, here's a summary that the doctor included. This is something I highly recommend you go through. I love it when Dr. Hannah puts summaries, because some lectures you can literally study from her summaries because they're very comprehensive, and I really like that. There was one, I remember a lecture in MOL 2, I forgot which one, but she gave us a really comprehensive summary, and alhamdulillah, it really helped. I really like summaries like that. This is a very scary picture. This is all of the pictures from the slides. This looks like a Lippincott kidney. I believe this is a summary from Lippincott. Now here's a summary I wrote. So first of all, we have purine de novo synthesis. The goal of purine de novo synthesis, we start off by making PRPP. We add atoms. Eventually, we get IMP. That gets converted to AMP and GMP. Purine salvage converts preformed bases into AMP, GMP, and IMP. AMP by APRT, GMP and IMP by HGPRT, and they all require PRPP. Pyrimidine synthesis takes less steps. It was 6, and it makes UMP. UMP is the parent. And the pathways are usually end product inhibited and feed forward stimulated. So for the steps that you had to know in detail, for almost all of them, they are end product inhibited or feedback inhibited. So that's a really good point to remember, because for almost all of these, and you can go back and look at what I said wasn't, they are end product inhibited, at least. Now, don't focus on all 11 steps of purine synthesis. You're going to waste your time. It's too many steps. You're not going to get it. Focus on the steps that we actually covered and that the doctor actually covered. Of course, remember the diseases and remember the drugs as well, because the beauty of this lecture is that we talk about things that can be clinically relevant. I put the diseases in my notes. If you click or if you put on escape, for example, you will see the notes section and you'll see all the diseases and all the details you need to know about them. All right, now we have questions. I have 3 questions to ask, and we'll be done. So first of all, dihydrofolate reductase can catalyze the reduction of dihydrofolate to tetrahydrofolate. Which of the following drugs is an inhibitor of dihydrofolate reductase and can be used in rheumatoid arthritis treatment? Who wants to answer this in the chat, or that's on mute? I don't mind. Just, I guess chat maybe. Okay. So Selma is saying D. Do you guys agree with her? All right. So you guys agree with Selma. Very good. You guys are correct. طيب. And I mentioned to you guys that in our exam, patients will have when someone is given methotrexate, they may have a deficiency. Do you remember what they could have a deficiency of when you give them methotrexate? Like which molecule they'll have a deficiency of? Folic acid, very good. Yes, folic acid is correct. Thank you, Sani. Next question. A 70-year-old male patient undergoing radiotherapy for prostate cancer develops severe pain in the metatarsal phalangeal joints of his big toe. Monosodium urate crystals are detected by polarized light microscopy in fluid obtained from this joint by arthrocentesis. The patient's pain is directly caused by overproduction of the end product of which of the following metabolic pathways? Like, who can answer this in the chat? Okay, so one of the 231 said C, another person saying C, a third person said C. You guys are all correct. Myclophenolic acid. Sorry, purine degradation. Yes. What we're looking at here, remember, I said crystals, old man, arthrocentesis, they're basically screaming gout in your face. And gout happens as a result of excess uric acid, and uric acid is a result of purine degradation. It is the end product of purine degradation. This is a very, very common way in which they ask questions. This may not be, like, for example, you may not get a question that's exactly like this. I try to replicate it as much as possible, but you never know. I do hope you get questions like this because you would have seen them. Last question. So a deficiency in the attached step would result in which of the following? So this is adenosine deaminase. If we have a deficiency in adenosine deaminase, what disease will we have? Which option? Okay, Senma is saying B. 231 is saying D. Okay, both of you write why you think your answer is correct. And if you don't know why your answer is correct, just say you don't know. It's fine. I'm just going to give you guys a minute to write. But in the meantime, whoever else wants to answer can answer. Okay. Okay. So yeah. So Selma is correct. The answer is B, severe combined immunodeficiency. And yes, it does. This reaction leads to decreased B and T cells. And it's okay that you mixed up, as I mentioned before, and I will continue to mention again. Get it wrong now. Don't get it wrong on the exam. The disease that causes, which enzyme causes Lesch-Nyhan syndrome? If you have a deficiency in which enzyme will cause Lesch-Nyhan syndrome? HGPRT, very good. HGPRT, which is involved in the salvage pathways, and the patients will have the symptoms of HGPRT. Characteristically, they will try to self-mutilate. Okay. That's it for the lecture. Thank you guys for your contribution. I really enjoy teaching this lecture. Some things I'd like to mention just before we go. Keep in mind that while this module is only 2 lectures, like nucleotide metabolism is only 2 lectures, this is 8 questions on your exam. Guaranteed, at least for us, it was a guaranteed 8 questions that you'll have. My advice is don't underestimate how beneficial this could be. If your MCQs have 80 questions, and 8 of them are these nucleotide metabolism from the nucleotide metabolism lectures. If you study this well, you've guaranteed yourself 10% of the exam, which I know may not sound like a lot, but in the long run, it really does help you. It's a very nice module. It's very good. It's very comprehensive, and I think that if you just go through it a little bit, you'll get it like this. All right. And I believe in all of you, inshallah. I do wish you all the best. If you have any questions, my email, my number is on the front slide. And these slides will be sent to you. I'll answer any questions you guys have now, but if you don't have any questions, feel free to leave. Thank you all very much. Okay, do we also make, oh, wait, there's a good question. Do we also make ribonucleotides and pyrimidines, or do we directly make deoxyribonucleotides? Really good question. To be honest with you, I'm not sure. With pyrimidines, I tried looking it up, for example, because there are some other things like, I didn't talk about pyrimidine salvage, for example. And I tried looking it up, and I eventually got a bunch of plant research. Regardless, I will look your question up and get back to you, inshallah. But yeah, so again, if you have any questions, do ask them now. If you want to ask me at a later time, feel free to do so. And thank you all for attending. Really appreciate it. Of course, again, Eid Mubarak, and have a nice day. Take care, guys.